Okay, hello everyone and welcome to our last content meeting of this year. Today's topic is binary search trees. They're pretty important topics that have a variety of applications, and they also come up quite frequently in programming interviews and sometimes in coding competitions, so it's nice to know them. So let's go ahead and I'll start screen sharing. There's going to be quite a bit of terminology in this meeting, more so than in previous meetings. So if you have a notebook or somewhere you can take notes and write stuff down, I highly recommend doing that because there's quite a bit to remember. And we'll also be doing some hands-on examples afterwards. So this over here is a diagram of a binary search tree. And a binary search tree is a type of binary tree. In a binary tree, you basically have nodes or values, like you can see over here, we have 8, 3, 1, 6, 10, and so on. And there are edges, these lines that connect the nodes to each other. So that's what a tree is. It's just made up of nodes and edges. And the number of edges is always going to be one less than the number of nodes. So you can see over here, I'm just eyeballing it. We have 9 nodes. We're going to have 8 edges in this tree, 8 lines. Now, a binary tree is a type of tree in which each node can have at most 2 child nodes. So you can see over here we have 8, and 8 points to 3, and it points to 10. The nodes that 8 points to are called its child nodes, and 8 is the parent node. So 3's parent node is 8, 10's parent node is 8, and the child nodes of 8 are going to be 3 and 10. So that's something you may want to write down. And in a binary tree, what I was getting to is that the most number of child nodes that a node can have is 2. So looking at this tree, you can see that the most number of child nodes any node has is 2. Over here, 1 has 0 child nodes. 14 has 1, just 13. 8 has 2, 3 and 10. And in a binary search tree, this is even more specific than a binary tree. In a binary search tree, the way that the tree is constructed is in such a way that for a particular node, all the nodes to its left are going to be smaller than it, and all the nodes to its right are going to be bigger than it. So let's start drawing on this diagram over here. Okay. Yeah. So if we look at the 8 over here and we look at all the things to the left of 8, so we look at 3 and then all this stuff over here, one thing you'll observe is all of these values are smaller than 8. Alternatively, if you look on the right side, the 10, 14, and 13, they're all greater than 8. And this pattern, this trend that we see is true for all the nodes. So if you look at node 3, everything on its left, the 1 over here, is going to be smaller. Everything on its right, the 6, the 4, the 7 is going to be bigger. And the binary search tree stores the data in this way so that it's quick to figure out whether you have a certain value in your tree. It's quick to add elements to your tree, to remove elements. It takes log n time. A lot of its operations are log n because of the way that it stores data. And if you're looking for 4, for example, if we're looking for the number 4 in our tree, we know that 4 is smaller than 8, so we're going to go to the left. And we have 3 over here. We know that 4 is bigger than 3, so we're going to go to the right to 6. And we know that 4 is less than 6, so we're going to go left to 6, and then we find 4 over there. So that's why it's log n, because in each step, we can split our decisions in half. And if this sounds familiar, it's because we covered binary search, which works in a very similar way. And that's also a log n algorithm that has the similar logic surrounding it. So that's what a binary search tree is and how it stores data. One last bit of terminology I wanted to share with you guys is a subtree. So this over here, this whole diagram we're looking at is a tree. A subtree is just a smaller tree within a larger tree. So for example, this over here is a subtree. And we call this 3's subtree because 3 is the node at the top. We call the node at the top the root node or the head node. 3 is the root node. And this is 3's subtree that I've just circled over here. And this over here is going to be 14's subtree with just 14 and 13. So are there any questions about the terminology or how binary search trees work? I'll pull up the chat just to make sure. Okay. So if there's no questions at this time, you guys should pull up whatever IDE you use to code because we're going to be doing some hands-on examples. And this is highly recommended because um, it's good to get practice in. And we're going to be covering quite a bit. We're going to be covering, so I'll be covering how to create a binary search tree and how to add nodes to the tree. Then Madhu will cover how to travel through those trees, access elements, print them out, stuff like that. And if you remember in the previous meetings, we've covered BFS and DFS, those algorithms. They can be applied to trees as well, in addition to grids. So we've done BFSs and DFSs with grids. Now we're going to do them with trees, binary search trees in particular. So I'm going to go ahead and get IntelliJ open over here. And you guys should also have something open which you can use to code. And I just have a basic class, it's empty, it just has a main function.
Ishan thought he was doing IJ apps.
Yeah, I said Android. I was about to say Android Studio. Yeah. So the question is now, how do we represent this binary search tree? Well, a binary search tree is just made up of a bunch of nodes. So what we're going to do in our code is we're going to have a node class. So outside of our main function, I'm going to type static class node. And let's think about what values we want to give this class. Each node has a value. So you can see over here, this has a value of 8, this has a value of 10. So we're going to say int value. Each node, like I said in a binary tree, is also going to have a node on its left and a node on its right. So that's why in our class, in addition to having a value, each node object is going to have a left node and a right node. Now we'll create the constructor for our class. When we want to create a node in our tree, we're going to give a value that we want the node to have. So I'll say int val, and it will say value equals val. And when we print out our node, we don't want it to print out the memory address. We want it to print out the value of that node. So that's why I'm going to have the toString method over here. And this is going to return value followed by an empty string. So I'll copy and paste this into the chat. This is our node class. And this 8 over at the top, does anybody remember what the node at the top of the tree is called?
You called it a root or a head?
Yeah, that's correct. So we'll go over here and we'll create a variable for our root or head node. So I'll say static node head. And inside the main function, I will give the head node a value. I'll say head equals new node, and I'll pass in the value 8. We're following this example over here. So our head node has a value of 8, and just to make sure everything's working, I'm going to print out the head node. And when I print it out, it's going to print out 8 because that's the value that that node stores. So I'm running the code, and you can see here, it printed out 8. That was the output I got. Is everybody at this step? Okay. Now that we have this, we're going to go ahead and learn how to add nodes to our tree. We have a couple of nodes over here. I'm just going to go ahead and create an array to make it easy to add nodes. So I'll just say int to add. This is going to be an array. And let's see, we're going to add 10 and 3, and then 14, 1, and 6, and then 13, 7, and 4. I'll just say 4 and 7. Or it doesn't make a difference. Okay. And the reason I put this into an array is because now I can just iterate over it and say int new value into add. So for each of these values in my array, these are the values I want to add into my binary search tree. I'm going to write an add function that will do this for me. So I'm going to write an add function, and this add function will take in the value that we want to add, which is called new value. And in addition to taking in the value that it wants to add into the binary search tree, it's going to take as its second parameter the head node, or actually as its first parameter. I'll just put it first. So there's two things we're passing into this add function. We're passing in our head node as well as the value that we want to add into our tree. And now we will write our add function. So once again, it's going to take in a node. I'll just call this node. And it's going to take in a value that we want to add. And now we've got to think about our logic. Let's say I have this tree over here, and I wanted to add the number 0 into the tree. Which direction would I go? Would I go left or right? You can type into the chat or unmute yourself. If I wanted to add 0 into this tree. I would go left. Because remember, the way that the binary search tree stores data is anything, if you want to add something less than the current node, you go to its left. If the value you want to add is bigger, you go to the right. So we'd go left. And then from 3, we would go left again. And from 1, we would go left again. And we keep going until we find an empty spot. That's important to note. We can't just say, okay, 0 is less than 8. Let's say the left node for 8 is going to be 0. It doesn't work that way because that spot is already taken up by 3. So what we have to do over here is we have to check if the value is, we'll consider the left case first. How did the 4 end up a child of 6? Yeah. So what happened was when we were adding, in this diagram, before they added 4 and they were considering where to add it, they looked at the root node. 8 is greater than 4, which means that 4 has to be added to 8's left subtree. 4 is greater than 3, so it has to be added into 3's right subtree. And 4 is less than 6, so 4 had to be added as the left node for 6. And that's how that happened, because 4 is less than 8, so we go left. It's greater than 3, we go right. It's less than 6, we go left. And that's how it ended up there. Now, in our add method, what we're going to do is if the value that we want to add is less than the current node's value, so if value is less than node.value, that means we want to go into our left subtree. But what we're going to do is before we even go there, if the node on the left is empty, like in this example, 1 doesn't have a left node or a right node. And so that's why we're going to insert 0 as 1's left child. So that's why over here we're going to check if node.left is null. So basically it does not exist, it doesn't have a value. Then we're going to say node.left equals equals new node. And then we say new node and then value. Because the node on the left is empty, it's going to create a new node and put it into the left spot. So 0 over here would be inserted as 1's left node because 1 currently does not have a left node. But let's go back up to this example over here with 3. Because 0 is less than 3 and we have to go left, and 3 already has a left node 1 over here, we can't add a 0 as 3's left node. That's why what we would have to, why did it do that? Okay, let me just delete this. That's why what we're going to have to do is we're going to have to add this value that we want to insert into the left subtree. So that's why we pass in add node.left. Because we know that the value we want to add is less than 8. So we have to add it somewhere on the left. That's why we call add node.left and value. And the logic is exactly the same if the value we want to add is greater than or equal to our node's value. So now this is the logic for the left subtree for adding stuff on the left. This is going to be the logic for adding bigger numbers on the right. I'll just go ahead and copy this because it's exactly the same, except what's the one thing that I have to change over here if I want to add stuff on the right? I'll give you a hint. If you want to add stuff on the left, we use a particular word. What do we have to say if you want to add stuff on the right?
We want to add it to the middle.
Yeah, we changed left to right. Okay. So this is our add function. Are there any questions about that? We'll go ahead and verify that it actually works pretty quickly. I'll copy and paste this into the chat in case you were not able to keep up. And if you want me to go slower, you can just let me know as well. So after our for loop and after we've added all these values um, to our binary search tree, Madhu is going to cover how to actually traverse this tree and access and print out all the values in it. So that's why we'll just do a very basic example. Let's try printing out the 6. If I wanted to print out the 6 using head, how would I do that? What would I have to say? Well, I'll start with the 3. How would I print out the node with the value of 3 over here? Instead of saying head, what would I have to use? I would have to say head.left. I'd print out head.left because 3 is on the left of 8, and you can see it printed out 3 over here. If I said head.left.right, it is going to print out 6 because head.left would be 3, and then the right of 3 would be 6. So does everybody understand the structure and the way that it works? But you can see that this is a pretty bad way of accessing values because we don't know if they exist. Like let's say I wanted to access 0. I don't know if 0 exists, but I'm going to try to see if it exists. So I'll say head.left.left. I'll use left 3 times. I'm going to get an error. I'm going to get null when I do that. And if I do head.left.left again, so I do it 4 times, now I'll get an error because I'm calling left on a null pointer, on a null object. And that's why it's important to know tree traversals, and these especially come up a lot on coding interviews which involve questions on binary search trees. So if there aren't any questions about this, I'll hand it off to Madhu, who will cover those traversals.
Can you let me screen share? I don't have permissions.
Okay, you can share now.
Okay. Can you see my paint?
Yeah.
Yeah.
So there's 3 different ways that you can go through a binary tree when it comes to reading like what elements are in the binary tree. And each of these 3 ways have their own purpose for like why you would want to read it in this specific way. So the first one I'm going to cover is called in order. So it's called in order. And the point of an in order traversal is to retrieve the values from the smallest value to the greatest value in this specific case. And that's usually what it will do. So the way that we can get the smallest value to the greatest value and get it in order is doing left, root, and right. And I'm going to explain how that works with this example. So we start off at the very top, which is our head node. So we start off at 7. And the first thing we're going to do is see if we can go to the left. So we're going to go to the left. And then now we're at this 1. So we're going to make sure that 1 isn't null. And since it's not null, we're going to try to go left again. So we're trying to go as left as possible. So we're at 1, and then we're going to go left. So once we get to the 0, we're going to try to go left once again. So if we go left, we'll find out that there is a null value here. Like there's no node that's to the left of 0. So as a result, we're going to print out 0. So our print will contain a 0 and a space. And the next thing we're going to do is, now that there's nothing to the left of 0 and we printed 0, we're going to check if we can go right now. So we're going to try to go right, but there's another null value here because 0 doesn't have a right node or a left node. So now that we've kind of gone through 0, we're not going to go back here anymore. So we're going to go back to our previous call. So for 1, we've already tried going to the left and we're done going to the left. So now we're going to print out that 1. So wait 1 second. Okay. So we're going to print out that 1. And now that we print out our 1, we're now going to go to the right of 1. And the next element that we're on is 3. So now that we're on 3, we want to try to go left. So we're going to go left and we're going to go to this 2. And it's a bit repetitive, but I'm just going to explain the left half of the tree, and then the right half of the tree, I'll explain the beginning. So it should be like a few more minutes for explaining this. So now that we're at the 2, we're going to see if we can go left. So if we try to go left, there's a null value because there is no node to the left of 2. and then after we see that there's no value to the left of 2, we're then going to print out that 2. So we're going to print out a 2, and then we're going to try to go right. So as you can see, we're kind of following this order of we try to go left first. If we can't go left, then we'll print out the root. After we print out the root, we'll try to go right. And we'll repeat these steps with this kind of order of priority. So after I print out 2, I'm going to try to go to the right of 2, and there is no value there. So I am done with this call of 2. I'm going to go back to my call with the value of 3, and I'm going to try to go to the right of 3. And I'm going to keep repeating these steps. So if I keep repeating these steps, I'll be printing out that 3 first, and then I'll print out 4, 5, and 6. And once we go all the way back to the top, once we're done with all of these all these calls of trying to retrieve these values, we're then going to go back to the top to the 7. So once we've gone to the left, so in this case, let's say we've already accessed all these values, we're going to print out that 7 and then go to the right and repeat our steps again until we're done reading in all the elements. So that's what an in-order traversal is. And the purpose of an in-order traversal is to get the values from the smallest value to the largest value. So here it'll print in 0 through 10 in order. So that's kind of where the name comes from. Another way of we'll do the code for in order first, and then I'll teach the other traversals for binary trees. So if you can go back to your IDE, we'll be coding out an order traversal. And yeah, if you have any questions, please list it in the chat, or you can unmute yourself. Okay, can everyone see my IntelliJ?
Yeah.
Okay. So we'll be coding an in-order traversal method. So you should just call your method like in-order traversal. So static void. And the reason we want to do a void method is because we'll just be printing out the values. We're not going to be storing it into a string. So static void in order, and then we'll just do the node. So if you remember, the first thing I always checked was if that node was null. So if the node is null, or actually, what's this? If the node, sorry.
I was just going to say that's a good way of doing it.
Yeah.
If node equals null, then just return.
Yeah. So if the node is actually null, we're going to return nothing. So we're just going to return nothing. Otherwise, what we're going to do is we're going to see if we can go left. So what we're going to do is we're actually going to make a recursive call of this method, but instead of just going to the same spot, we're going to go to the left node. So what we're going to do is in order node.left. And what this will do is it will kind of repeat the process like I was doing on MS Paint earlier. And once we go left, once we go as left as possible, and we can't go any more left, what we're actually going to do is we're going to print out that value. So if you just type in system.out.print, don't do print line, just do print, because we want to have our entire traversal be printed onto one line. So just print in node.val, or the value of the node, and then just put a space. And once we print out that value, if you remember, we then went to the right of that node. So we're going to recursively call this method, but instead of doing node.left, we're going to do node.right because we want to go to the right this time. So that's actually all there is for the in-order traversal. And all the other traversals are very similar, except they have their own specific order for different reasons. So to test our code, we're going to go down to the bottom to our main method, and we're just going to do call the in order method. So in order head, because we want to start at the very top. So that's why I'm using head as my parameter rather than any other of the elements. So I'm gonna run my code, and it should print out the values from one. Depending on however this is done, it'll print out the values in order. So as you can see, the values are printed from the smallest value of 1 all the way to the biggest value of 14. So that's the use of in-order traversal. And the next traversal I'm going to cover is pre-order and post-order. And both of them are very similar to in-order, except they have their own use. So we're going to go back to Paint. So I'm going to speed through this a bit because pre-order and post-order are actually very similar to in-order. It's just a different, it's just a bit different in how it's going through the elements. So we can see my paint, right? Like the nodes. Okay. So what's different about pre-order is that it will actually go from left, or pre-order will go from root, left, then right. And the purpose of pre-order traversal is let's say you wanted to create a duplicate of a binary tree. That's the main use of pre-order traversal. So the way we're gonna go through our elements here is we're gonna start with the root and then go left. And then once we go left, then we're gonna go right. So initially, one second. So initially we're gonna start at our 7 and we're gonna print out the 7. So here we're gonna print out a 7, then we're gonna go left. So now we're at 1. What we're gonna do is we're gonna print out that 1 and then we're gonna go left. We're gonna print out the 0 and then we're gonna try to go left again. And since there is a null value here, there's nothing to print. So the next thing we're gonna do is we've already gone left. And what we're going to do now is we're going to we're going to try to go right. But there's another null value here. So since there's a null value here, we're just going to go back up to the call with the 1. And we've already gone left. So the next thing we're got to do is we're going to go right. So now that we're at this 3, we're just going to print out this 3. And then we're going to go left. So once we go left, we're at the 2. We're going to print out the 2, and then we're going to try to go left. Left is null, right is null. We're going to go back up to the 3. We've already gone left, so now we're going to go right. So once we're at the 5, we print out that 5. And as you can see, it's a very similar process. And once we're done with all these elements, we're then going to go to the right of the 7 and repeat the same process. So as you can see, it's a bit similar to in order, except it just follows a different order of operations, kind of, if you want to think about it that way. And I'll be showing the code for that on IntelliJ. So get your IDE back up. And we're going to code in the pre-order method. If I'm going a bit fast, please let me know in chat and I can explain it a bit more slowly. But I explained pre-order traversal a bit faster because it's very similar to in order, in my opinion. So create your method static void. And the reason we want a void method is because we're just printing out things. So we don't need to return anything. So static void pre-order. And we want to have a parameter called node. And what we're going to do is we're going to check to see if the node is null or not. So if the node is equal to null, we're just going to return nothing. Otherwise, we're going to then try to we're going to print out the node, and then we're going to try to go left and then try to go right. So very similarly to our in order method, we're just going to print out the value of the node. Make sure to do print, not print line, and then have a space. So if you guys remember, once we print out the root value, what's the next thing we should do? It's if someone wants to type it out in chat or unmute themselves.
One hint, it's either left or right.
Yeah, 50-50. Yeah, okay, that's correct. You go left. So what we're going to do is we're going to recursively call the pre-order method, and we're just going to do node.left. And once we go left, after we try to go left and there's nothing to do when we go left, we're then going to go right. So pre-order of node.write. And that is going to be the pre-order method. So to make sure I did this correctly, we're going to print out the pre-order traversal. So what we're going to do is we're just going to have a system.out.println, because this in-order method doesn't have like an extra line at the end. So if you were to print both of them at the same time, it would all be in one line. So I'm just going to have this print line to separate the in-order traversal from the pre-order traversal. So I'm going to type in pre-order ahead, and then I'm going to run my program. So as you can see, it printed the pre-order traversal of our tree. Pre-order traversal doesn't have as much use compared to the other ones, but pre-order traversal is used to, if you want to duplicate the binary tree, that would be like the most practical use of a pre-order traversal. The next one I'm going to go over is, and the last one I'm going to go over is post-order traversal, and this one is actually a bit more useful compared to pre-order traversal. So back onto MS Paint, we're going to go over pre-order traversal or post-order traversal. So we're not going to be looking at this anymore. We're going to be looking over post-order. So what post-order traversal is it's left, right, then root. And the point of a post-order traversal is if you want to delete elements from your binary tree, because what this does is it will try to go one by one to each of the leaves of the tree. And why this is useful is because like if you want to delete an element, you want to first check the leaves, because you don't want to you don't want to remove a whole branch, for example. You would want to first check if it's in the leaves. If it's not in the leaves, then we'll be looking into the branches. So that's why you want to use post-order traversal when it comes to removing elements, because you want to remove a leaf rather than the whole branch if possible. So like if you remove this 9, that means the elements 8 and 10 will just disappear. And we want to what we want to do with post order is make sure that that 9 isn't actually one of the leaves, because we would rather remove this than remove this, which will cause the removal of the 10. Because if we remove that 9, the reason that these elements will disappear is because 9, 8, and 10, their parents are 9. So if we remove that 9, 7 won't have a right node at all. And without a right node, that 8 and 10 will disappear with the 9. So hopefully that makes sense. And I'm going to go over post-order traversal. I'm going to go over it a bit quicker. So once we're at the 7, what we're going to do is we're going to go left if possible. And then after we go left, we're then going to go right. So once we go left, we're going to go to this 1. We're going to then try to go left. So to left is 0. We're going to try to go left. There's nothing on the left. There's nothing on the right. We're going to print out that 0. And what we're now going to do is we're going to go back to this 1. We're not going to print it. We're going to go right first, actually. So we're going to go right to this 3. And then from the 3, we're going to repeat a process. We're going to try to go left. We're going to go left. We're going to get to the 2. We're going to try to go left. There's nothing on the left. It's just a null value. Then we're going to try to go right. If there's nothing on the right also, then we're going to print out that 2. I'm sorry if it's a bit repetitive, but I hope it helps with explaining how the traversals work. So once I printed out that 2 and I've gone left and right, then I'm going to go back to this 3. Then instead of printing out that 3, I'm going to go right. So I'm going to go to this 5. I'm going to try to go left. I'm going to go to the 4. Then because there's nothing underneath, I'm then going to print out that 4. And then I'm going to go back to the 5 once I've tried to access the left and right elements of 4. So now I'm going to go right to the 6, and then the 6 will get printed next. And once that 6 gets printed, then the 5 will get printed, because after 6, so before this, because what happened was the element 5 called the post-order traversal of 6. But because there's nothing to do with the 6 afterwards, it's then going to go back to the 5. So it's going to go back to 5, then it's going to go back to 3, then 1, then 7. And oh, it's not going to go back to 7 actually. It's going to go to 7 last because it's going to do the post order traversal of the right side. And once that's done, then the 7 will get printed at the very end. So I'm going to show the code for this. If anyone wants me to slow down, please let me know in chat and I can slow down. But now I'm going to show the code. So get your IDE back up, and I'm going to cover the post order traversal code. So it's going to be the same as all of our other traversals. Like the overall code is the same. It's just the ordering of that code is slightly different. So what we're going to do is if node is null, return. Return, it will just do nothing. Otherwise, what we're going to do is we're going to do post order. We're going to go left and then right. So node.left. And once we've gone all the way to the left, we're going to check if we can go right. So post order of node.right. And if there's nothing on the left or right, or if we've already accessed all the values on the left and right, we're then going to print out that element. So what this will do, so I'm going to repeat this once again. The point of post order is to access the leaves of the tree, like the most outer elements of the tree, before printing out the roots of those branches, if that makes sense. So we're going to print out node.value plus a space. And what we're going to do is in the main method, just copy over the system.out.println, and then we're going to write post order from the head. And if we run our program, it should print out the post order traversal of our tree. Oh, I did print line. I should have done print. So to just edit our code a bit, what we're going to do is I'm just going to add some labels. So in order traversal, and then there's that, and then I don't need this print line. So I'm just going to put a label on each of these traversals so you know what traversals what. And I'll post this in the chat very shortly. So that should work. What's wrong with this?
Return type is void, so you would have to print.
Oh, okay, I see why. 1 second. I'll just have to do print line, right? And then, okay. Wait, oh, in order traversal, and then have this. Okay, I'll post this in the chat in a second. And that should work for printing out each of the traversals. Yeah, it works. Well, I would have to fix the new line, but we want to do the BFS and DFS right now, so I'll just post in the code in the chat. So, and then we can work on the BFS and DFS. So here's the code for all the traversals, and here's the main method. Oh, this should say print line. That's why it messed up.
Okay, I'll take over control really quickly before handing it off to Kanishk.
Yeah.
So we've covered BFS and DFS in the past, but they've been limited to doing work with grids. And BFS and DFS can be applied to grids, trees, graphs, all sorts of data structures. And Kanishk will be covering both of these algorithms, so it'll be sort of like a review. And just to give a quick recap, remember BFS goes level by level, so it would go like, it would start at the 8 and then go 3, 10, 1, 6, 14, 4, 7, 13. But the way that DFS goes, it would go 8, 3, 1, then 6, 4, then 7, then 10, 14, 13. It goes all the way down. So just keep that in mind as Kanishk starts to teach you guys about that. And Kanish, you can go ahead and start screen sharing.
Okay. So we'll be building off of what Ishan did with his add class and his node. So if you've already coded binary search trees like Ishan did, the only difference here is that I have some different values for the head node and the nodes to add. And also, because we'll be looking at the depth of various nodes throughout the tree, in your node class, we currently have the, the instance fields of value and left and right nodes. Just in there, also add int depth. So I'm going to paste all of this in the chat if you guys didn't get it the first time with Ishan. So basically the only differences are I have different values for the array, for the nodes that are added. And when you look at the order in which these nodes are added, you can sort of visualize what it would look like. So our first node is 5, so that would be in the middle. Then because 4 is less than 5, it would be to the left. And because 6 is greater than 5, it would be to the right. And we can go on and on with all of these. So I won't go through all of them, but this pixelated representation is what the tree looks like right now. It has 5 at the top because that's our head node. And then it goes in this structure. And the numbers inside are these values that we added into add. So the two ways we're going to go through this is first through DFS, then with BFS. DFS is like it's an acronym for depth first search. So in DFS, you first like go all the way as deep as you can go, then consider other paths. So in here, we would start with the root node or the head node, then we would go left and keep going left until we hit a null. Sort of like how Madhu did with his traversals. We would keep going in one direction until we hit a null. And then after that, we consider the other path. So after we go all the way left, then the next path is to like see if this has a right, or this has a right, or this has a right, or this has a right. Then we consider the other path. So we go right, and then we first look at left and see if we can go any left, and we can't. We can't go any right. So basically, DFS goes as deep as you can go in one direction, and when it can't go any more, then it goes in the other direction. Like I'll go here, here, yeah. And now we can start coding this. So I'm assuming that everyone has all of this code copied. So yeah, I'm gonna create a new method called DFS. So it's gonna be public static void DFS. And this method will take in one node, so the node root. And first, and one more thing, I forgot this. I made one modification to a node class, which is I gave it a depth parameter. So we also, when we create this head node, we also need to, or initialize its depth parameter. So we gave head the value of 5. Now we also need to set head's depth, so head.depth is equal to 0.
Oh yeah,
Because head, yeah.
I'm just going to quickly say that we're doing a DFS to find the depth of a node, and we forgot to define what depth is. It's basically how many levels down you have to go from that root node. So for example, 3 has a depth of 2 because you have to go from 5 to 4 to 3. 1 has a depth of 4, 7 has a depth of 3 as well, or 2 as well. Yeah, like condition drill. So that's what we're trying to print out.
Yeah, I should have said that before.
No, I
But
should have gone over. It's fine.
yeah, so we just want to print out the depth of each node. So to that, we need a starting point, and our root node has a depth of 0. So that's why we're initializing with the depth of 0. So as soon as we reach a node, we want to first print out its depth. So to do that, we can do system.out.println, do root.toString. So this will get the value of the node and put a space. And then we give root, then so we're pairing the value of the node with the depth of the node. So instead of toString, I could just do value, root.value. Wait. Oh wait, it's not a method. Root.value plus the root.depth. So after we print that out, we need to do our DFS. And DFS, like I showed here, we first went left, then we went right. So we first need to check if we can go left, if a left exists. So if root.left is not equal to null, then we'll do, we first need to set the left's depth to this current depth plus 1. So you see, if a parent node has a depth of 0, then both of its childs have a depth that's 1 greater. So we can say that root.left, its child's depth, is equal to the parent's depth, root.depth, plus 1. And then we can do DFS on it. We can call this recursively DFS root.left. That's DFS for the left side, and for the right side, it's the exact same, except you need to change one word in all of them. You might remember from Madhu's examples that instead of left, we just change it to right. And that is our DFS method. And to call it, we just need to do DFS, and we give it our root or head node. So we do DFS head. And if we run that, please run. It will give each number and its depth in DFS order. So like we showed in here, it should first go all the way to the left. So it should be values 5, 4, 3, 2, 1 with depths 0, 1, 2, 0, 1, 2, 3, 4. And we can see that it's that case. And then it accesses the rest of them as well. That is DFS. And I will post this function in the chat if anyone's behind. Are there any questions about this?
I have a question for you guys. If we've covered DFS, what comes next? What are we covering next?
Review.
Okay, just making sure you guys are still here. Yeah, that's correct.
So now that we've done DFS, we can do BFS. And fun fact, you can't do breadth first search with recursion. Fun fact. So if we wanted to do BFS, well, let's first define, oh wait, let me first show you how it would look like on this. So we would start at the root node, and remember BFS uses a queue, and as it accesses the queue, it adds on the next elements that we want to search through to the end of the queue. So we would first add the root of the queue, process it however we need to, then add the left node of it to the queue, and the right of it to the queue. In the beginning, there would just be 5 in the queue. We would process it, then add 4 and 6. Then once we take out 4, we would process it, then see what we can add to the queue, which is 3. And then we would look at the next thing, which is 6, process it, and then add the 5 and the 7 to the queue. So in this way, we're going outwards at the same pace in all directions. And that's what the name breadth first search sort of implies. So let me first define, like Ishan said in the chat, you could do sort of a level order traversal. There's some LeetCode questions on this if you guys want to try it out. So public static void, we'll call this BFS. And this will also just take a node root. And like I said, we're going to need a queue for this. So queue, and the queue will have node types, node objects in it. We'll just call it queue is equal to new. And you can implement a queue on different data structures, and I just like doing it on linked lists. Right now I'm getting red errors because I haven't imported Java util. And then to start with the queue, we need to add in the root or head node. So queue dot, not head. We need to put the root node in. Oh wait, it is that. Put is for maps. And we continue this process of adding to the queue, processing the nodes, and like dequeuing them until there's nothing left in the queue. That's when we know we've visited every node. So our while function, it'll keep going while the queue is not empty. So while queue is empty not. And first, we need to take off a node off the queue. So we'll call it node poll is equal to queue.poll. And we can also, the depth of that node is just poll.depth. And then like in DFS, we first print it out, then we check the left and the right, and if they're not null, we will add them to be processed. So we can just copy this here and say system.out.println, and the node we just got was called polled. We change that to poll.value. Instead of root.depth, we would use polled.depth, which is just depth. Now we've done this first part. Now we have to check left and right. So if polls.left is not equal to null, then again, we need to set the left's depth to 1 more than what it is right now. So poll.left childs.depth is equal to the current depth, the parent's depth, plus 1. And then we just add poll.left to the queue. And then we do the same thing with the right side. And we just replace all the lefts with the rights. And that's it. So if we call this method, we do BFS on head, and I'll put a separator here. Just say BFS and run this, we can see the difference in the processing order between DFS and BFS. And let me just post the code in the chat. So in the DFS, the depths weren't really in order. They were going like all the way down first, then up again. We went 0 all the way down to 4, and back to 1 and down. But in BFS, because it's going in all directions at the same time, the depths are all like grouped together. And we can sort of see that that's how it should be in the BFS tree. Like we would first start with this, and we would process these 2 nodes, then these 3, then these 2, and this one. So are there any questions? Oh yeah, one thing. Normally, when we did BFS in a grid, we had a visited like array or map or something. We don't really need a visited in this case because trees only have pointers in one direction. So if they had a pointer in the other direction as well, then we might need visited. But because you can only go one way, we don't need any visited or anything. Yep. That's it.
Yeah, guys, so that's it for today's meeting. Thank you so much for coming. If you're a junior, we hope to see you next year or back at one of our meetings for the APCSA exam review. And if you're a senior, we wish you all the best. Thank you to everybody for coming to our meetings. I know a lot of you have been here since the beginning of the year and come to almost every single one of the meetings, and we appreciate that. If you have any questions, you can stay behind. Otherwise, you're free to go. Bye.
Bye.